Hear that? You good? What about now? Oh, a little more. People picture pins pitter-pattering on a plate is pretty tough. Yet you, youth and youth of yore, yield to the tink, tink, tink of this tiny tools tango on the tabletop. As the sewing stick strikes the steel, it shakes, sending out a sound so soft, it's synonymous with silence. But it sends a sound all the same. Now, it's hard for even an engineering physics sophomore like myself to really appreciate all that's going on when I drop a pin on a piece of metal. The pin falls due to gravity, hits the metal, and the metal shakes, ever so slightly, but just enough to jiggle the air around it. This air jiggles the air around it, which jiggles the air around it, which jiggles the air around it, which jiggles around it, all the way up until the air inside your ear is jiggled. Yeah? Hand signals going on in the background. Anyway, this air jiggling inside of your ear jiggles the eardrum, and you perceive it as sound. Now, a pin dropping is just the tip of the iceberg when it comes to all the interesting things we can learn about sound. But before we get into that today, it's my job to remind you of some pieces of equipment that will be necessary. Now, these devices, there are two, are some of the oldest physical instruments that are in this room today. I know us physicists use them every day. In fact, we all do. But I bet Tim Chubb thinks that I turn mine off sometimes. These instruments are composed of thousands of pieces, all working in perfect unison to allow you to perceive the world. And you would think that such elegant instruments would be beautiful, simple, extravagant, but they look like someone chewed up a bunch of bubble gum and stretched it over a seashell and strapped them to the side of your head. Does anyone have a guess for what these are? Anyone? Don't be shy. Ears, yes, your ear. Now, I have a huge ear with me today. No man, woman, or child designed the ear, and, well, hopefully someone designed that ear, else there's something out there. I don't want to see it. Nature designed the ear in a process called evolution. Now, if something as complex and useful as the ear evolved, it must be pretty useful. So I ask you, what are some uses of the ear? Why do we have ears in the first place? Raise your hand if you think you know something. Yeah? To hear, yeah. Your ears are to hear. I've never tried seeing with my ears, but I don't think I could. Yeah? To gain information. Information, that's a good one. Avoid danger. Yes. Anything else? That's a good line of reasoning based on the evolution stuff I said. I came up with a few. One is, as you said, dangers, lightning, bears, etc. We were once living out in nature. Another is communication, like talk we're given today. I send out information, you receive that information and are able to act upon it. You can't do that without hearing, setting aside sign language. Another is finding resources. When we lived out in the wild, it was useful to hear a babbling brook, or if berries made noise, I guess you would hear the berries. And, of course, to hear the sweet, sweet sound of the hit single Good Vibrations by the Beach Boys. Now, these are all very different sources of sound, but I'm pretty sure if I played the sound of the thunder's roar and I played you the sound of Good Vibrations, you'd be able to tell the two apart. But we don't stop to think very often about how we can tell the two apart. What's different between a thunderstorm and Good Vibrations? Does anyone have any idea? Yeah? Thunderstorms are louder. Very good. Wavelength. Someone's been studying up. That'll come up later today. What else we got? Anything? I'll give you a hint. Actually, I'll save it for later in the show. But, I already started talking. Now I got to tell you. You can play the same note on a piano and a violin, and they sound different. That's not loudness or wavelength. And we'll explore that today. Two of the most basic that I came up with are volume and pitch. Now, I think we're all pretty familiar with volume. Things can be either loud, but in case you don't know what loud means, I'd like to ask, on the count of 3, everyone yell, "Good job, Ian." Okay? Ready? 1, 2, 3. Good job, Ian. Thanks, guys. You shouldn't have. And of course, things be quiet. Good job, studying wearing physics crown. But, especially you kids, might not know about the concept of pitch. Now, pitch is how high something sounds. For example, I might scream in a really high pitch that my clicker's not working in the presentation. A bird's chirp. A bird's chirp is high pitch. You can hear the tweet, 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 but next, a gorilla. Pretty low pitch. Oh, okay, enough gorilla. Now, these are a lot of different sounds. You're going to hear a lot of sounds in the show today. And before we get into all these sounds, I would like to test your ability to perceive pitch. Now, I assume if you can hear me up until this point and you haven't said anything, your volume's working just fine. So we're going to test your pitch today. To do that, I'm going to start playing a sound, and you raise your hand when you can hear it, and then drop your hand when you can't hear it anymore, and we're going to see who puts their hands down when. Ready? All right, let's hit the sound. I haven't played this sound yet, guys. You guys should know better. Jeez Louise. Apparently, studying physics for 8 hours a day tampers with your ability to follow instructions. Let's hear the sound. Now pay attention to the room. Very good. Who's going to be the first? Got some down. Okay. There goes Professor Tim. Very nice. I'm impressed. Now take a look around the room right now in particular. Remember this. All right, I know you two kids are lying because I'm lying about my hand. I stopped hearing it a while ago. Now, when I told you guys to look around the room, what did you notice? Anybody? Age. That's something. So, as you age, all the parts of your ear, go back one, accumulate damage. I have a little ear up here. Sorry, low pitch scream. I'll worry about that later. I have an ear up here. If you can see it, you can see the eardrum in here, ear bones, and then this is the cochlea. Cochlea with tiny little ear hair cells in it, and those are what detect the sound. All of those get worse as you age. Your eardrum thickens, your ear hair cells bend and they break, and your bones lose range of motion, so you stop being able to pick up on the high pitch. But what's interesting is you all could hear the low pitch. There's an asymmetry there. Your ear is worse at picking up the high pitch because a high pitch, as you'll learn, is a very fast shaking of the air in your eardrum. It's really throwing the eardrum around, and it's hard for bent, broken pieces to keep up with that. Here's a graph with each curve represents age. Let's see if the laser pointer works. Oh, well, now the clicker's working. Each curve represents age, and you can see frequency versus the hearing threshold, which is how loud it has to be before you hear it. Now, when you're young, it's pretty flat. Like, you can hear all the way up to 8,000 hertz like any other sound. But as you age, up here in the high frequencies, it has to be really loud for you to even pick it up. This is a man and a woman, and it's about the same. With this test, I think that's all you really need to know for the rest of the show. The limits of your lobes and how to handle heaps of hollers. If I leave you with a piece of device today, it's use both and listen close. Thank you and enjoy the show. Is this here?
Ian, hi everybody. Ian is a engineering physics sophomore, and he also works in my lab, which is why he makes fun of me. Hi, I'm physics professor Tim Chupp, and I'm going to start my part of the show to welcome you actually with a riddle. All right, who can solve the riddle? I don't want to see all the same hands here. Yes, what's the riddle? Pi plus 1, exactly. Okay, right. So welcome, fellow nerds, to this. All right, I want to welcome everyone. Who's here for the first time to a Saturday morning physics? All right, well, welcome. There's a group of people here in the front of the room who put their hands up, and they are visiting the University of Michigan as prospective graduate students in physics. So we want to give them a very warm welcome to encourage them. So they know what a wonderful place this is, and it is. Okay, so I want to tell you about Saturday Morning Physics. We're coming up on 30 years of Saturday Morning Physics. Saturday Morning Physics started in the fall of 1995, and it was actually started by a young assistant professor at the time up there, is Dan Amadei, who came here from Fermilab. Fermilab is a picture of the Fermilab accelerators from the sky is shown in the green. And this was modeled in a way on a program that was developed by Leon Lederman, who was a Nobel Prize winner, a director of Fermilab, a wonderful educator, a very warm human being, and he told the best jokes and did the best job of telling those jokes. So it was actually first designed to give postdoctoral researchers experience in giving talks and teaching and so on, and they gave a little lecture series of 3 lectures. The first one was actually someone who worked in our laboratory, Robert Welsh, and a few years later we followed with a spring series that were given by professors, and I gave the first one of those on nuclear magnets. So I've been involved in this program for the whole time, and for about the past decade I've had the privilege of being one of the faculty leaders of the program, along with this year Professor Rachel Goldman. But it's evolved, and one of the turning points in our evolution was when we had the opportunity to interview and meet with Josh Cassada on the space station. Who was involved? Who came for that event? that sort of changed our perspective. We realized how important Saturday morning physics could be as a family-friendly venue as well. So we've added these, and that's what we have here today. But it's also evolved to be not just physics, many things. So STEM, science, technology, engineering, and mathematics. And in addition, the relationship of all of those to everyday life, to art, to policy, etc. So Saturday morning physics is become quite a thing. Now, this, I'm going to let you know that to put these on is not trivial. There's quite a number of people, and I'll introduce you to Monica here, Wood, who's the head of the demo lab. And today, we've really put Monica and her staff, Nick, Arnold, and Connor Heaney, to work for all of the demos that you will see here in the room and also in the gallery, hands-on things afterwards. We also have, I'm not even going to list them right now, but the second line there gives you the named endowed support for Saturday morning physics, but a great deal of our support comes from gifts and from you as well. So there's more information about giving and supporting Saturday morning physics and keeping us sustainable at saturdaymorningphysics.org. And Giving Blue Day, a university-wide fundraising effort, is this coming Wednesday, and the physics department is featuring Saturday morning physics. So again, you can go to saturdaymorningphysics.org to learn about it. And today we are also introducing to all of you the STEM-mobile project. So STEM, science, technology, engineering, and mathematics, and mobile, helping it be, get on the road, putting it on the road. So our ambition is to outfit a vehicle so that student groups, many of whom will be represented in our presenters today, can take what they're here to teach you here today on the road throughout Southeast Michigan to schools, to libraries, and to events throughout Southeast Michigan. So we're very excited about this. Many of us are working very hard on making this a reality, and this is kind of our kickoff event. So that's where we are, and that's why we have the STEM Mobile. Okay. The cast and crew is listed here. You'll meet many of them here in the room today, and many more of them in the gallery, hands-on gallery afterwards, which will run until 1 o'clock. So. All right. Oh, my. Wait a minute. Monica did just change the screen. Let me see. Does anybody notice? Well, it's hard not to notice, right? Because I made you look at the screen. I said, look at the screen. Everybody look at the screen. Okay, what do you notice? I can't. Yes. What do you notice? You notice something you're calling sound waves. Why do you call them waves? Because they're sort of, well, kind of wiggling, like waves wiggle. Maybe not like waves that you'd want to surf on. Okay, cool. What else do you notice about those waves? Changing, okay, that's a big word, amplitude. But something's changing, right? And when I talk very softly, like Ian was trying to do, when I talk very softly, they're not very big. But when I talk loudly, they fill up the screen, right? So this is a device that somehow is connected to my microphone. The microphone has, well, it's not really an eardrum, but it's just like an eardrum. It's a membrane that vibrates and turns that into electronic signals, and those electronic signals are being sent to the apparatus that Monica is standing next to. It's called an oscilloscope, but really what it displays along the bottom is time, I really have a sonorous voice when I finish my sentences. You can see that here. Whoops. Okay. And then on the vertical axis, as you saw, is basically how loud it is, or the volume. All right? So this is one way of looking at representing a scientific instrument that helps us display what's going on with sound. And now we're going to learn more.
Hello, everybody. Can you hear me okay? Good. My name is Ben. I'm a junior studying astronomy and astrophysics here at the University of Michigan.
And my name is Raven. I am also a junior at U of M studying astrophysics and physics.
We are here today representing the Student Astronomical Society. I'm the president.
And I'm the treasurer.
And out in the gallery, our vice president will be doing an experiment, so make sure to go find her. Today, we are going to give a little presentation about what physically is sound. Obviously, we've talked a little bit about the instrumentation, right, the ear, but what is sound and how does it work?
We've heard a little bit about how sound is a wave. Some of you may be familiar with this concept, but some of you may also not be. This mic is going in and out. So we're going to start by explaining what exactly a wave is.
Sorry, guys.
Okay. Is this better? Can you hear me? Okay, great. We're going to start by explaining a little bit about what a wave is. So the definition of a wave is pretty simple. A wave is simply something, a change in a physical property, and a wave also travels with a finite speed. And that speed kind of depends on what type of wave it is, which is also something we will explain.
Now, for our first experiment, we are going to need a volunteer from the audience. Is anybody interested in coming up? I see a volunteer right here. All right. If you could make your way to Raven. So, we are going to be using this slinky in order to model some of the different shapes that a wave can take. First off, I'm going to need you to really quickly just flick the slinky. Even harder. Whoa! Too hard!
You're strong, you're strong.
Right in the middle. Did everybody see that?
Yeah, that's a good one, that's a good one.
The wave you're creating is actually moving up and down the slinky. This sort of wave is called a transverse wave. Now, for our second wave, we're going to need you to bunch up a whole bunch of slinky into your hands. There we go. All right, on the count of 3, we're going to let it go, all right? 1, 2, 3. Did everybody see the difference there? The actual disturbance, the oscillation, was in the density of the slinky. It was the compression. This sort of a wave is called a longitudinal wave or a compression wave. Now, question for the audience. Does anybody know which of these sorts of waves sound is?
It's a compression wave.
It is a compression wave. When we think about a speaker, right, blasting music, you feel a little bit of buzz, but you don't see the speaker jumping up and down. It is a compression, a longitudinal wave. All right, everybody give our volunteer a big round of applause.
Wait. I want to just encourage for future volunteers. Here's a T-shirt for you.
Now, there are 2 types of waves. We've talked about the shape, now we're talking about the type, the physical type. These are mechanical and electromagnetic. Sound is a mechanical wave, but not in the way you might know the word mechanical. There are no pistons, no cogs, no gears. You wouldn't take your sound to a mechanic.
So the difference between electromagnetic waves and mechanical waves is that mechanical waves need something to move through. And the thing that a wave moves through, we call a medium. A good example of this that I'm sure you're all familiar with is waves on water. If any of you have been to the beach, at an ocean, or a lake, you'll know that when waves move through the water, it's actually the water itself that's moving when the waves go. And that means that water is the medium for waves in an ocean. Sound waves are also mechanical, like Ben mentioned, which means that they need a medium to travel through as well.
Now, I'm going to make maybe a bit of a dated reference here. Only the most ancient members of our audience might understand this. It is a really, really old movie, but bear with me. Has anybody ever seen the film Alien? Yeah, we've got some oldies in the audience raising their hands. That's good. Alien isn't exactly the most scientifically accurate movie. I've never seen a xenomorph in real life. But the tagline, "In space, no one can hear you scream," is actually scientifically accurate. In a vacuum, like space, where there's no air for the sound to compress, there is absolutely no sound. Couldn't hear you scream, couldn't hear a pin drop, nothing. Now, in order to kind of show off this effect, we are going to use the bell and light bulb in a jar at the end of the table here. So everybody pay attention as we turn it on. Can everybody hear that bell? More or less? Good. Can everybody see the light bulb? Awesome. We are now going to pump the air out of the jar. What do you hear now? What's changed? There's almost nothing. The bell is vibrating the table a little bit. That's where you're getting your leftover sound from. But otherwise, without the air, sound can't travel.
Now, did anyone notice if the light changed at all? Do we still see the light? We see the light. That's because light, unlike sound, is an electromagnetic wave. It doesn't require a medium to travel through. So even though there is no air in this jar, we can't hear the sound, but we can still see the light.
We're going to let the air back into the jar now. There's a vacuum inside now, so it's a little hard.
It's a little hard to pull off.
And the air comes rushing back into the jar, and the bell is back to normal, and the light bulb remains unchanged. And we will shut off the bell now. Now, I'm going to play a video for you. We are going to see a flash of lightning and hear a burst of thunder. And I want you to pay attention to when you notice both things. What did we notice? Yes.
The sound came much after the actual lightning.
It absolutely did.
Yes, the sound came after the lightning. And this is because sound takes time from when it is emitted to reach your ears. It has to travel through the medium before it can reach your ears. And it travels at a very specific speed, called the speed of sound, appropriately. It's called CS. It looks like we have a little bit of a formatting error there, but it's called CS.
And this sound is significantly smaller than the speed of light. I know it might be sort of hard to believe that sound does this. You can see my mouth moving, and then you hear my voice pretty instantaneously. But that's because the speed of sound is actually almost 400 meters per second. And for our Americans in the room, that's a lot of football fields.
The speed of sound also depends on the medium that it is traveling through. A great example of this, which you might not expect, is that sound actually travels about 5 times faster in water than it does in air.
And if you want to measure the speed of sound yourself, Jen is going to be hosting a demo out in the gallery where you can measure the speed of sound, hear it, measure it. It's going to be great. That's all we've got for you. Thank you, everybody.
So let me try to fill the silence here a little bit. So what did we learn just now? Sound needs a medium, and the medium for the sound that's coming from me to you is, right, very good. Okay. Are we ready? Awesome. I've had the privilege of working with 14 undergrads and graduate students in physics and astronomy and engineering. So it's really been tremendous. And now we have Sophia and Katya, who will.
Yes. Hi, you guys. Oh, there we go. I think I've.
Sorry, guys. That was the other one that was on the other side.
You'd think with a sound show that we wouldn't have so much trouble with sound. But we'll get there.
Okay, yes. Thank you guys for your patience. My name is Sophia Davis. I'm a senior here at Michigan studying astrophysics and museum studies, and I'm also joined by...
I'm Katya. I'm a fifth-year astronomy PhD student here.
Perfect. Well, we are going to be getting into the concept of measuring sound. And we can do that through this concept called sound spectroscopy. And Katya is going to walk us through this.
All right. So, I'm going to start this going. All right. All right. So, everyone, look at the screen. What do you see? A mess, right? Like, what is this? So you guys remember how Tim and Monica were showing you your sound waves, right, through the oscilloscope? You saw a one-dimensional representation of that sound wave. Now you guys are seeing a two-dimensional representation of a sound wave. So we're going to look at a little bit more complicated of a plot here. So what I want to do is just do a little experiment, right? Make some noise. Woo! All right, yes, you identify your sounds in there. So you saw how it got really, really dark up there? Yep. So that means that the noise was really, really loud. So now I want to do another experiment. Can you guys make me a really low-pitched noise? All right. Now a high-pitched one. All right. So what you're seeing here, right, on this plot is we have time going, right, on the bottom. And when you made a low-pitched noise, right, you saw a lot more dark color in the bottom here, right? When you made a high-pitched noise, it got a lot darker near the top of the plot. And so this plot is what we call a sound spectrum or a sound spectrogram. And it lets us actually visualize the sound waves that you are hearing in a two-dimensional format. So, there we go. What exactly is sound spectroscopy, right? That's a fancy term. All spectroscopy is, it's just a technique that we use to analyze waves. So you can use this to analyze light waves or sound waves. And all you're doing is you're breaking up those waves into individual frequencies or wavelengths. So think of different pitches, right? If we're talking about light, right, very similar to how if you have a prism, it takes light, goes through the prism, and you're breaking it up into its different colors of the rainbow. Works the same way with sound. We're just breaking up a bunch of sound into individual frequencies or individual pitches from low to high. So, what do we actually use sound spectroscopy for, right? This sounds like a very complicated sort of thing that only as physicists or only scientists would use. We could use it for music, right? Can anyone think of anything else? What? Birding, yes.
That's a good one. That's a great one.
Any others? No? Glaciers, yes. Those are really good examples. Yeah, it's hard to come up with at first, right? You think music is like the most obvious sort of thing. Voice recognition, yes. Submarines, exactly.
Absolutely.
Yeah, up there. Yep. Yeah, up there. Medical ultrasound. All right. Yes. Seagulls. Yeah. Also birds.
Yes, we could also do that.
Yeah. So, right, you guys have pretty much named all the examples we're coming to think of. Linguistics also, analyzing speech patterns and sounds of different languages. Gravitational waves. You guys, how many of you have heard about gravitational waves discovery? Yeah, okay, a lot of you, right? You guys all go to Saturday morning physics. You know about it. And so, is it coming up? Yeah, actually, gravitational waves were discovered using this sort of sound spectrum technique where you can actually hear the chirp of the two black holes merging together. And so on the screen on the left, there's a one-dimensional picture of it. And then we actually made a 3D model of the gravitational wave signal. So after the show is done, you can go check that out, play around with it, touch it in the gallery. All right, what else do we have? Ecology, yeah, so whoever mentioned glaciers, good job, yeah. Listening to the sounds of nature, soundscapes, how things like airplanes or jets affect natural landscapes. And also medicine, so ultrasounds, just like someone else said. Man, you guys are the experts in sound spectroscopy already. All right, so now we're gonna switch back to our sound spectrum program, and I have some tuning forks here. And so I want you guys to pay attention to what you see when I sound these tuning forks. All right, our thing's still going, cool. So I have here a C, if any of you are into music, so do. I'm just gonna sound it and see what happens. All right, what do you guys notice? Yeah, shout it out. Yeah.
It makes a gigantic vertical line in the bank.
Yeah, exactly. It makes one big line. So right up here, this big line. Now, instead, I'm going to play the note G. And now look what happens. So we have another vertical line, or horizontal line, sorry. Now, what happens, right, if I play these two together at the same time? What do you notice there? Yeah, there's two lines, exactly. So each of these tuning forks are special because what they're making is what we call a pure tone. And so this is when you have something that's emitting sound that is only one frequency or one pitch, right? This is just the pitch G, this is just the pitch of C.
But wait, Katya, we were talking about music earlier. Is that just one
We were.
frequency?
That's a really good question. And you know, I'm kind of tired of tuning forks.
I'm getting a little tired
Yeah,
too.
maybe instead we should actually play some music.
I'd be
right?
down for that. Yeah, absolutely.
So,
We would like to introduce our physics jazz band. If our
come on up.
if our folks would like to come
on up. Woo! Need my guitar.
Oh, wait. It
Uh-oh.
looks like we're missing an instrument. We don't have anyone to play the
We have
piano
a piano
for
right
us.
here.
Would anyone like to volunteer to be a part of our physics jazz band?
You don't actually have to know how to play piano.
You gotta hit one note.
You gotta hit one note. Yeah. Way up high.
Up there? Oh,
Way
yes,
in the back.
Yes, come on, come on.
Yeah.
Thank you, yes.
Woo!
I was gonna have the mic real quick to introduce her. Hi. What's your name? Molly. Well, Molly will be our pianist for today. Thank you so much for volunteering. I'll show you over to your instrument. All right, you got it. Perfect. All right. So we're gonna do a run through of each of our instruments, make sure we're in tune and everything with each other. Sound good?
All right.
Clarinet, are you ready?
Look at the screen.
And Molly?
Beautiful.
Perfect. Yeah. All right, now let's play all together, right? You
all
can play
together.
the same note all together.
We're playing a C, by the way.
All right. And now also notice, right, where is my, oh, there we go. Right? So remember, I had a tuning fork that was a C, right? So let's play it. All right, so you notice, right? The horizontal line that you see coming from the tuning fork at the same exact place as the rest of our instruments. But what did you notice when we played our instruments as compared to the tuning fork? I heard overtones,
I saw a hand over there.
harmonics. Yeah, over there. What? Different frequencies, yes, exactly. So when we play our instruments, we don't just get one tone, right? We don't get pure tones, we get a combination of tones, right? So we have a pure tone and, as someone mentioned, the harmonics. So actually, let me show you, there we go. Here's just pictures of what these spectra actually look like. And so you can see that all the different instruments have lines that are kind of all multiples of each other.
But remember, whenever we were looking at that tuning fork, it made just one clean line on the spectrogram. How can we be playing the same note, but we're resulting in different shapes like you guys just saw in the previous slide? Well, with the tuning fork, like we mentioned, it's a pure tone, so only one frequency, nothing extra. But whenever, that doesn't quite fully explain why these different instruments are playing the same note, but sound different. But if I say hello and
Hello.
and Katya says hello, you can still tell it's me that's speaking. Why? Well, everyone has a unique voice, and it's just like instruments. Even if a clarinet or a violin or a piano all play the same note, they sound different, and that's because of timbre. So timbre is the quality of sound, and it's unique to the material, the size, and the shape of the instrument itself. And so we can think of timbre as what makes each instrument sound unique, even when they all play the same note. But what actually causes these differences comes down to the fact that, comes down to the fact of, that whole concept of timbre. And I remember we had some people mentioning overtones and harmonics, and that's exactly what's coming into play here. And now I know those were kind of big words, but imagine you drop a ball. You're gonna have your biggest, slowest bounce, and that is gonna be the fundamental frequency, otherwise known as the main note that you hear. But as the balls keep bouncing, there are these smaller, faster bounces on top of it. And you can think of those as the harmonics or overtones or those extra frequencies that shape the sound. So whenever we were looking at all the different spectrograms of each instrument, we noticed that there were different lines that followed the fundamental frequency or the main note. And that's why instruments sound unique even if they are playing the same note. But wait. Does anyone hear that? Does anyone recognize what that sound could be?
Bird. Yeah, you're hearing a bird.
Actually, I saw a couple of these birds on the diag today.
Yeah. So who here likes birds or bird watching? Raise your hand. Oh, a lot of you. Okay, that's great. And now, how many of you have ever used an app or something to go outside and identify what bird you're hearing based on their call? Yeah, a couple of you. If you haven't, would recommend. It's really fun. But what you just heard, right, as a bird sound, there we go. That was actually an American robin. And so you can actually take that bird sound and turn it into a spectrum, the same way that we were turning our instruments and our voices into spectra. And this is actually the way that your phone app identifies what bird it's hearing. It'll actually go and make a spectrum like this and match it, try to match the how the spectrum looks, right, its shape, to each different bird sound.
And if you really want to test your knowledge from this portion of the show, you can find some sound spectroscopy demo out in the gallery where you can match bird sounds to the resulting spectra. And I know that we've mentioned optical spectroscopy as well, and there will be a demo for that if you would like to decode the hidden colors and light.
Yeah, so can we thank everyone who participated in our physics jazz band? Thank you. Yeah.
Thank you, Molly.
Yeah, we have to thank Molly, too.
Oh,
Yeah,
yes.
thank you, Molly. Woo!
Yes, but with all of that said and done, we are going to move on to the next portion.
Okay, thank you, Sophia and Katya.
Hey everyone, I'm Andrew. I'm a sophomore studying physics and math, and
I'm Ishan. I'm also a sophomore studying physics and math.
today we're going to be talking about standing waves, waves that are standing still.
And you know, we physicists, we're really bad at naming things, but in this sense, standing waves are just that. They're just waves that stand. And they're unlike the waves, you know, like Ben and Raven talked about that we're propagating. They literally just stand here. And to demonstrate that, I would like a volunteer. So does anyone want to? Yeah, you can, right there. What's your name?
Oliver.
Oliver? Oliver, I'm going to make you do something very complicated. You see this switch?
Yeah.
And you see this knob?
Yes.
I'm going to make you turn on that switch and move that knob. As much as you want to go. And look at what we're seeing here. So those waves that we talked about, well, we're seeing those waves right there, right? As Oliver is showing. And oh, look at that. And as he turns up the speed or the frequency of this motor, we're seeing those wavelengths like compress and like shorten. And as he keeps going, the wave like amounts and wave numbers we have keeps increasing. Do you want to keep going, or you want to see how far we can go, Oliver?
How many we can
Yeah.
straight to max. No problem.
All right. I think our super proprietary high material rope can only take it that far. University of Michigan sponsored and produced, guys. Can we get a big hand for Oliver?
So, as we've seen throughout the talk, we know that sound creates waves in air. And because of that, we can also expect that sound creates standing waves in air. So I'm going to try something. There will be a noise if, I don't know, we're hearing a lot of noises, so.
If this is giving you modem flashbacks for the older audience, we apologize.
I'm just going to ask you guys to all sit still and then slowly move side to side.
Get
Very
one
slowly,
hand,
just a
one
little
finger
bit.
in your ear.
Plug
About
an ear.
8 inches in distance.
Plug one ear.
Plug one ear while you do it.
No, whoa, 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 whoa. You guys are going to knock heads together if you're not careful. We have to do this in unison. So that way first, slowly, and then that way. There you go.
Now move back and forth. If you can, try to move up and down, but I know you're all sitting, so. So what we saw there is there are two speakers here that are emitting sound waves, and they're separated by some distance. And what that means is that, as we saw with the rope, there are areas where there are peaks and there are areas where there are troughs. There are areas that are like louder and quieter as these two waves build on each other. And what you're doing is these standing waves exist throughout the room, and you're moving between the louder areas and the quieter areas and the louder areas. You're moving throughout this standing wave pattern that exists in this room.
And that is actually something called interference. So the way this rope thingy works is it shoots that like pulse and it bounces back. And that bouncing back, like those waves actually like talk to each other and they add up and subtract. And what's really cool is that they literally just add up and subtract. So these like peaks here, those are like the noisy parts. And these like small nodes, they're the silent parts. So that's the parts like, you know, you can't really hear well. And these are like the high energy, you know, these are the peaks.
Okay, in addition to air being a nice medium for sound, natural gas is also a nice medium for sound. Monica, would you mind helping me? As an aside, I could have completely bombed this presentation, but I get to play with like the coolest demo. So it's all fine in the end. So now this is a speaker, and it's going to vibrate this rod that exists, and there's natural gas in this tube. And what happens is we'll see there are standing waves created in the fire that shoot out from the tube. Yeah. Really is an awful sound, but I think it's pretty cool. We see, I can't talk while that sound's playing, so maybe I'll just talk now. You see that there's standing waves created in the fire, as there are compression waves, sound waves, pushed through the natural gas that exists in the tube. And that's just from this speaker. The speaker vibrates, it compresses the air, which compresses the air, which compresses the air. And then we get those peaks in fire. And so there only exists a certain range of frequencies where this can work based on the materials and the gas and the fact that, this is a certain length. But yeah, I think that's the coolest demo. Okay. Here I want to go into a bit of an aside. We've been talking about sound waves, but I wanted to mention another type of wave, light waves. And microwaves, I'm sure most of the people in this room have microwaves in their home. They shoot microwaves through your food. And they shoot back and forth throughout the food. And a lot of us have noticed that when we cook things with microwaves, there are areas that are really, really hot and areas that are really cold. And you really have to, cook for 30 seconds, rotate it a little bit, or shift it to the side. Get a nice even cooking. This was just a Getty images that I found, and you can tell it's burnt, and then less burnt in other areas. And this is just due to standing waves. The microwaves shoot from side to side, and they create standing waves throughout the microwave oven, and that means there are areas that are hotter, there are areas that are colder. And if you have a nice microwave that has a rotating plate, you're just rotating food through that standing wave so that it cooks a bit more evenly.
So, again, your microwave is just this guy. It's just this rope guy. But this is where your cold food is, where your food that's not tasty is here. And this is where the really tongue-burning food is. And, I'm not going to move this guy, but this guy has wheels right here. I don't know if you can see it. And that's what your, microwave plate is doing. It's, moving your food around so that, these node guys can chill, and these, anti-node guys, the peak guys, can come at your food, too. So your food gets an even cook that way. That's why we have the spinny thingy.
That's all for us. Thank you, guys.
Thank you.
Okay, great. Thank you. Thank you, Ishan and Andrew. And we have one more part of the show.
You got the clicking?
You have the clicker?
I don't know. All right, so Andrew and Ishan gave us a nice visual representation of what a standing wave looks like. But now we're going to see what it sounds like. We have a contraption over here called a Hoot tube. And by all intents and purposes, it just looks like a normal metal tube, but there's actually a little bit of metal mesh located at the bottom. We also have a fire source, which I personally think makes this the coolest demo. And we're going to heat this tube up, see what happens when we hold it vertically, and then rotate it and see what happens when it's held horizontally. This might take a second, so bear with us. Maybe turn the fire up. Yeah. And turn it back up. Whoa. So what exactly is happening here? Well, the physics behind this is very, very similar to the system of a fireplace and a chimney. So we have our fire source, you can see over here with this Bunsen burner. It's heating up the little metal piece of mesh that I mentioned at the bottom of the tube. And when this heats up, it heats up the air around it. And as we know, as air increases in temperature, it expands. So the air at the very bottom of the tube is of higher pressure than the air at the top of the tube. And this pressure difference causes the air to start moving upwards and out of the tube. And this movement of the air molecules is what we call a convection current. As it turns out, a convection current is just a standing wave, which Andrew and Ishan introduced to us in the previous section. And that's all cool. I think this demo was super cool, but what if we have an even bigger fire source and an even bigger Hoot tube? What do we think will happen? Can we get a couple shout-outs from the audience? How do we think this system will compare to the smaller Hoot tube that we experienced? Louder? I'm hearing louder. Anything else? Deeper. Okay, maybe it'll make a deeper sound. Well, the great thing is that we can just test it and see. Let's turn it sideways. Let's try that again. Whoa, okay. So for those of you in the crowd that said it made a deeper noise, you were right. And we're also witnessing a couple different things happening. So you notice that when Sophia was holding the tube vertically, the tube was able to vibrate and make noise. That's because of that convection current that I mentioned earlier. But as it turns out, when we turn the tube horizontally, it stops the current from moving, and those air molecules aren't able to vibrate the tube and make the noise. And we also have that with this larger tube, with this larger system. The standing waves that we're experiencing have a longer wavelength and therefore a lower frequency. So we're hearing a lower pitch note over here. And this very much has to do with the concept of resonance, which my colleague Sophia over here will give us an introduction to.
So every object has its own resonant frequency, which we can actually hear it. Oh, sorry. Every object has its own resonant frequency, which we can actually hear in this glass when we flick it. Sorry, hold on. So, we also know that sound is a bunch of vibrations moving through a medium. So, what happens when the sound interacts with an object? Well, it's kind of like a swing, where the object is moving at its resonant frequency, and the sound is giving a push to the swing. If the sound is moving at a resonant frequency at the object's resonant frequency along with the object, then it's like you're pushing the swing at the correct timing. So when the swing's at the top, you're giving it a big push forward. And when the sound's at a higher volume, it's giving more energy into the object. And that causes the object to shake. So over here, we have a little demonstration. We have our wine glass up at the top and a strobe camera so you can see what's going on. We also have a speaker right next to it. And this speaker will play a sound at the glass's resonant frequency. And when the volume is turned up, you'll be able to see the shaking happening. So.
All right, let's try turning up this volume a little bit and focus on that center screen. This is an overhead shot of that wine glass.
You might want to plug your ears.
Oh yeah, it's gonna get a bit loud.
jiggling happening on the left side.
Wow, that was pretty cool. But Sophia, I'm kind of curious. What do we think would happen if we turned the volume all the way up?
You know, I'm not sure. I think we should have an audience member come try it out. You want to come down in the pink?
Oh, no. I don't know. It's fine. Okay. Hey, we could have 2 audience members help us with this task. Yeah, give them a hand. Okay. Your names? Name introduction.
What's your name? Nico.
Nico. And what's your name?
Evelyn.
Evelyn. Okay, so Nico and Evelyn are going to help us out with this task. We can only have one of you guys touch the button. You want to touch the button? Okay, and we're going to stand over here and maybe, we can have both of you touch the button. Okay, so what we're going to do is, before you put those headsets on, I'm going to show you there's a volume button over here. And when we give you the go, you're just going to crank it up to max volume. Now, these are because it's going to get quite loud. You guys are going to be standing closest to it. I'm going to be a bit further away. And for those of you in the crowd, watch the screen, or if you can see this, watch over here, and we're going to see what happens. And just make sure you stand on this side of this plexiglass. Yeah, put those headphones on. Okay. And then when you guys are ready, you see the knob with the pink tape. You can turn it together.
Great.
Thank you. Okay. Thank you, Evelyn and Nico, for your help. Good job, guys. Oh, and we have T-shirts for you if you would like. Thank you for participating. Cool. Thanks. Oh, yes. Okay. So this is what happened to the glass. It's now broken. A before and after, if you will. Cool, so that was our piece on resonance. We are wrapping up the show now, so we're gonna give it off to Tim for the final remarks. Thanks again. I'm Trisha, this is Sophia.
Okay, well, that's our show. Just a quick review, and I want to invite everyone to join us in the gallery, which is running on the first floor of the entire building. There's a whole number of hands-on activities led by our crew here. Let's give them a great hand again. And several others. So we'll see you there. Thanks for coming, and I hope you enjoyed the show.